Dear friends, welcome to this electrical engineering knowledge sharing channel, AMP Power System. Today we are going to discuss workshop 5, session 8. In this session, we will be discussing about overhead conductor details and the selection procedure. Otherwise, we can say another way, fundamentals of the or basics of overhead conductors and the various factors which affect the sizing of these overhead conductors and how we do the sizing of overhead conductors. This will be discussing under this session 8, but as it will be more than 1 hour, so I have planned to split into two parts, part 1 and part 2. In part 1, we will be discussing about the overhead conductor basics or fundamentals, and part 2 will be discussing about the various factors which comes into play to size the overhead conductor and how to do the calculation. So now when we are going to discuss about the overhead conductors, the first part we have already discussed about the cables which we lay either above ground or underground or through the conduit or through the duct bank, all these things. Now question is why overhead conductor we use. Now our ultimate goal is transmitting and distributing power to various consumers in a most safest way with a cost optimization, with a security and service to be continued. That is the main purpose of any electrical transmission and distribution. That is to maintain the security, to maintain the safety, to make it most optimistic, cost-wise optimistic, technically optimistic, and to maintain possibility to keep the provision of suitable maintenance and easy installation and maintain the system, not to disturb the system or not to stolen the system, not like that. So to achieve all these things, in some situation where the cabling system is not appropriate, in which case this may happen, suppose a long distance, suppose 100 kilometer distance from the source or the generating station, power to be transmitted 100 kilometer away. In that, on the way this 100 kilometer, there are so many things. There are some forest, there are some rivers or canal, there are some mountain, and there are some paddy land. All these things are involved. In that case, if we want to take this power by cable, so there are a lot of negotiations is required. First of all, this land which is belonging to paddy land, belonging to the local farmers, so there will be dispute when you'll be digging the land or taking the cable, all these things, that will be a problem. In the mountain, taking the cable is not easy job. You cannot do in the mountaineer area. Through the forest, if you take the cable, then that is also a problem. So in this type of situation, we cannot use the underground cable or above ground cable. Above ground cable is not coming into picture at all. By underground cable, not possible. In that case, only solution is overhead conductors. And in this case, overhead conductor is easy to install, number one, and easy to supervise. If there is any fault or anything, immediately you can visualize. But in this type of difficult locality, where the forest, mountain, river, all these things, if there is an underground cable, and if there is a cable fault is there, it is difficult to identify, and to repair is also very expensive. So this type of situation, we cannot go by the underground cable. Similarly, in the rural distribution, in the village power distribution, nowadays, rural electrification is one of the government main objective in all country. Now this rural electrification is supported by whom? Either by government of the respective country or by World Bank. They are supporting this type of project. So this type of project, first of all, it should be technically viable project, and cost-wise it should be optimistic, as it is done by government fund or by the overseas fund. To make this optimistic, in the case you see the rural electricity distribution for the village or farmers, now the villagers in a village, in particular one village, how many people are living? How many families? Maybe 25, 30, 40, 50 families are living in one village. Then maybe another village, maybe 5 kilometers away, another village, there maybe another 25 families are living. So in the case of rural electricity, the power requirement for each house, first of all, the requirement for individual house is very less. In the rural area or in the village area, if you go somebody's house, maximum there is some lamps are glowing and some fans are running. That is only the electricity consumption. They don't have all this refrigerator, all this high consuming light, they don't have. And that is also very limited number of houses only. So in that case, if you want to take by cable, this is not a very cost optimistic way. And taking the cable in the rural area, there is no proper provision for taking the underground cable, or there is no permanent road is not there, or the metal color road is not there, where the provision for the cable laying provision is there, and all this thing is not there. Maybe a small clay road or this raw road is there, through that you cannot take the cable. So in that case, only easiest way to distribute power and or to reach power to the remote end, to the this type of local consumers, is by the overhead conductors. That will be easy to install, and then you can easily monitor it, and immediately you can give a connection easily. That is very easy. But if you want to do this by cable to give a connection from the cable is not very simple. If you take an underground cable, suppose this is a ground level to surface level, and cable is going through this. If you want to distribute the, suppose there is a 3 houses over here, you want to give a power distribution to them, then you have to take this underground cable to the surface. You have to put a splitter box over here, or a junction box, where the inlet cable will be connected, and then it is a tee-off, and it will be again continuing, and there will tee-off supply will be given to these consumers. Similarly, again it will be going. So every time this type of arrangement should be there with the distribution box, with the breaker or some fuse. The arrangement should be there. So in case of rural distribution, this type of arrangement is not very cost effective, and maintaining this asset is also difficult. In the rural area, the electricity board people, they are not moving continuously. This type of item will not be there. Today you install it, after 6 months this equipment will not there. It will be stolen, it will be broken, then it will be damaged. All this thing will be there. So maintaining this property also very difficult. So this type of case, we cannot use this underground cable system. We used to use the overhead conducting system. So there are similar different arrangement is there. Suppose secondly, for for a particular cross section of the conductor, for the either is copper conductor, power carrying capacity of overhead line is more than that of the cable due to insulation or the cooling effect. All this, when we see the current rating of the conductor, we will see that open conductor current rating at a particular condition is more than that of the cable. So overhead conductor can carry more power than this normal cable, and in the normal cable there is a limitation of the voltage also. Though 400 volt kV voltage cable is to 400 volt 400 kV cable is there, but overhead line is easier to install and maintain for the maintaining and supervision also easier. So that's why for the high voltage transmission and distribution as well as very rural distribution, we use always this overhead line or overhead conductor. In the medium voltage level and in the plant electricity distribution, we use mainly the cabling system. Cabling system we mainly use in the urban area, I mean city area or town area or suburban area, where the high density population is living. Continually people are living in a high density population. In that area, overhead conductor is a safety issue is there. Then the current power carrying capacity limitation is there. In that case, we use underground system. So mainly underground system you can see mainly in the urban and suburban area, but in the rural electrification and high voltage transmission and distribution system, most of the case we use the overhead conductors. So that is the best of conductor. And advantage of overhead conductor is it can taken from the river, it can take through the forest, you can take to the mountain. It will be easy to install, easy to maintain, and if there is a fault, easy to identify the fault. And only disadvantage, there are a couple of disadvantages also, like suppose there is a thunderstorm, then it will be immediately subjected to thunderstorm. There is a storm, then the branches or trees are fallen on the circuit, then the circuit will be tripped. This type of disturbance is there. Then if it is exposed to the pupil, then pupil will be get injured, electrified. Suppose then another problem, if the overhead conductor passing through residential area, there is a limitation of the building height. If the building is below the transmission line, high voltage transmission line, you cannot go the building height up to beyond certain height. So there is a height limitation. Then also if it is near to the high voltage transmission line, there is a health issue may be there. So there is a certain distance to be maintained from the high voltage line to the residential area. All these disadvantages there, but still considering the power handling capacity and transmission, installation, maintenance, supervision, overhead line sometimes preferred in comparison to the cabling system. That's why overhead line we always use. Sometimes most of the time for the high voltage transmission, distribution, rural electrification, we use the overhead conductors from low voltage up to the 700, 760 kV or 1000 kV voltage we can use. We use these overhead conductors. Now, when we use the overhead line, then we have to look into this It needs like a cable has a conductor, it also needs a conductor. Now what type of, there are so many conducting material is there, like silver, gold, platinum, copper, aluminum, all are conducting material. But we have to find out a material which is a cost wise optimistic and which is economical, as well as which has a good conductor, which is good mechanical strength. So considering all these aspects, mainly two conducting material we use for the current carrying purpose or the overhead conductor purpose. One is a copper, another is a aluminum. These two material only mainly we use for the overhead power purpose. Now the copper which we use, that is not the normal copper. Actually this is called annealed copper. You know, annealing is a process by cooling and heating. We change the copper properties. Its strength can be increased, its ductility can be increased. So that type of annealed copper we use for this purpose. So this annealed copper conductivity, as per International Annealed Copper Standard ISCS, we call it 100% conductivity, that is annealed copper. With this we compare the conductivity of other material. This annealed copper is 100% conductivity and its mechanical strength is not bad. When we select any conducting material for the transmission distribution purpose for the overhead conductor, couple of properties we need to look into. One is the conductivity of this, number one, that will give a high current carrying capacity. As the conductor will be string between these two towers, so we need a mechanical strength. If this conductor has a poor mechanical strength, then it will be easily, it can turn out. Then it should be very lighter, because otherwise the sag will be very high. If the sag is more, then not only heating will be more, voltage drop will be more. If the conductor is lighter, then the sag or the depletion from the normal level will be less. That is also one of the requirement. Then it should be corrosion. If it is a lead, if this overhead line going through the corrosive area, then corrosion should not be more. So it should be corrosion resistant material. From considering all these points, so if we consider copper has 100% conductivity as per ISCS table, then it has a good mechanical strength. It has and another point, it should be resistant, because there is a I2RT loss, heating loss in the copper, in the material, in the conductor. So this conductor should be low resistivity and high conductivity. Copper has a very low resistivity and it has that means it has a high conductivity. Its mechanical strength is the middle class. It is not very low, not very high, but its specific gravity is very high. So in that case, what will happen? Due to high specific gravity, the weight of the copper will be very high. That is one of the disadvantages of the copper. And copper is expensive than other aluminum, other material. Other means aluminum or the below grade conductive material. Considering all this point, copper is nowadays we use for the underground cable in the cabling system, but for the overhead transmission line, and this copper is expensive, there is chance of theft of copper, because copper has a high scrap value. So if the copper conductor is there, it is get theft, then it will be sold in the market and it will be huge loss. Considering all these things, copper is not a very preferential or the preferred conductor for the overhead transmission system, except in some cases like the overhead train lines or tram lines, where the solid conductor is required to move with the pedal. In that case, we use copper wire. Otherwise, for the normal electricity transmission and distribution, either in a low voltage or high voltage, we do not use copper, because copper is expensive and it can get theft easily. And due to high specific gravity, this hanging distance cannot be very long. It should be short distance. Due to this, copper is not very preferable. In absence of copper, there is another material which we can use, that is a aluminium. Now the aluminium advantage is, this aluminium, the pure aluminium which we use normally, that pure aluminium we call is a 1350. That is the pure aluminium. This aluminium, its conductivity is not like a ISCS 100% copper, but it is about 60% conductivity in comparison to annealed copper. If annealed copper conductivity is 100%, aluminium 1350 conductivity is about 60% is the conductivity. Now, if you go the specific gravity of the aluminium, it is a very less in comparison to copper. So you can string the copper conductor in a long distance between the two towers. You can make the long distance between the towers. Then the copper has a mechanical strength, is about 50% mechanical strength of the copper. This aluminium about 50% mechanical strength of copper. And then this aluminium, another advantage is aluminium is as the specific gravity is low, I have already said, you can put a long distance for this aluminium. Now, some of the properties which is poor in aluminium, that that can be improved by using alloy aluminium. You know, this aluminium, we can make aluminium alloy, mixing aluminium along with magnesium and silicon. We call one alloy aluminium alloy. This alloy usually, this is a maintain the code 6201. By adding this magnesium and silicon, what has happened? This aluminium low mechanical strength in comparison copper, that can be improved by 50%. If this pure aluminium, that is 1350, if its mechanical strength is X, the mechanical strength can be improved to 1.5x by adding this magnesium and silicon. But by adding magnesium silicon, the conductivity is slightly reduced. This conductivity, pure aluminium conductivity is 60%. When we add this magnesium silicon, conductivity come down to about 50%. So 10% conductivity will be reduced, but the mechanical strength will increase by 50%. So that is one of the advantages of aluminium alloy, using aluminium alloy. That is also we use sometime in the conductor. And third conducting material which we use, that is we call is a cadmium copper. Now the copper, you know, the point is copper mechanical strength. If we want a copper to be used in the very corroded area or polluted area, in that case we said that pollution resistant material is used. Copper is not very pollution resistant, but if the copper mixed with cadmium, not only about 1 to 1.5% cadmium, if you mix with the copper, then it calls cadmium copper. That is called cadmium copper. By adding this 1 to 1.5% cadmium, immediately mechanical strength of this cadmium copper about 50% higher than pure copper, that is 150%, and this conductivity is reduced about 15%, so it becomes 85% of ISES rating. So if the anneal copper is 100%, the cadmium copper conductivity is about 85%, but its mechanical strength increased by 150%. And another important aspect of that, it is very corrosion resistant. So in the corrosion area or the high polluted area, we can use this cadmium copper. And this cadmium copper has a another advantage application is the breaker contact. You know, the breaker moving contact, due to high mechanical strength, this corrosion and erosion is very less. So in that case, the breaker contact, auxiliary contact, in all those cases we can use the cadmium copper cadmium. So this is the three type of conducting material we can use for the electrical power transmission and distribution purpose. Now these conductors, this material, either you use copper or aluminium or cadmium copper, we do not use a single conductor, because single conductor has various disadvantages. So that's why this conductor we use in a different form. Now the various conductor which we use, it has a market name. We call all is a AAC, all aluminium. One type of conductor we call is AAC. It is called all aluminium conductor. All aluminium conductor. Second we call triple AC. It is called all aluminium alloy conductor. All aluminium alloy conductor. Alloy, we have said how we get the alloy conductor, by adding magnesium and silicon with aluminium. We get this AAC. Then another conductor we call aluminium conductor steel reinforced, and another aluminium conductor alloy reinforced. These are the mainly four type of conductor we use. One is a AAC, all aluminium conductor. Triple is AAC, all aluminium alloy conductor. This is the aluminium conductor steel reinforced. Aluminium conductor. I am coming how it is. Aluminium conductor is steel reinforced. And this is a aluminium conductor alloy reinforced. These are the four different type of conductor we use. Here AAC means it is pure 100% aluminum, that is 1305, 1350. This is the grade of aluminum we use over here. And this is called aluminum, pure all aluminum conductor. Here all aluminum alloy conductor, here we use that aluminum mixed with the magnesium and silicon. That alloy we use for this purpose, for this conductor. And for when you make a aluminum conductor is still reinforced. In this case, what is I have already told that aluminum has a poor mechanical strength. To increase the moment you increase the mechanical strength, what we do centrally, we put one steel galvanized steel conductor, steel conductor at the center. Along the center we put the aluminum conductor. So this center steel conductor, that is galvanized steel, this galvanized steel has a high mechanical strength. So is automatically conductor mechanical strength get improved. So you use this AC, that is called aluminium conductor. Outside wall are aluminium conductor, but center there is a steel conductor, steel conductor or steel wire. That is a high mechanical strength. That is a galvanized steel wire. And in case of aluminium conductor, alloy reinforced, instead of steel wire, if you use a alloy aluminium, which we use that aluminium alloy, then we call it a aluminium conductor, alloy reinforced conductor. So these are the mainly four type of conductor. Out of this, ACSR conductor has a high mechanical strength and good conductivity, because the center point is your steel wire reinforced is there. That's why this mainly all the high voltage or medium voltage transmission and distribution, we use all aluminium conductor. Where the long string length is there, long tower length between the two tower, if the distance is high, in that case we use ACSR conductor, where you need a high mechanical tension or mechanical strength. But if the span between the two tower is not very, in the case of rural distribution, where the distance is not very long, or in the urban city, in case of urban city, though we use the cable, some of the urban area or suburban area, you can see there is overhead conductor is there, and in the urban or suburban area, houses are continuously one after another. So in that case, the tower distance is very less. In that case, you don't need more mechanical strength. In that case, we can use the all aluminium conductor or AAC conductor. But when the long distance is there between the two towers, suppose there is a river crossing or there is a mountain, in that case we use ACSR conductor always, even in the low voltage system. This AAC1, AAC conductor, these two conductors generally we use in the low voltage distribution in the rural area or suburban area or urban area. But when this long distance transmission is required and the long span distance is required with high current capacity or high power transmission, in that case you always use ACSR conductor, aluminium conductor is still reinforced. That is called ACSR conductor. This is generally you always use. So these are the four different type conductor. Now this conductor, how it is made? This conductor is not one conductor. This conductor is, suppose a particular current carrying capacity, a conductor is required, suppose 50 square millimeter. We do not make this 50 square millimeter one conductor. Why we do not make one conductor? Because there is a called skin effect. In the case of skin effect, what is happening? Suppose this is a conductor cross section area, this. Now this is the diameter of the conductor. Now when the current carrying through this conductor, there is a magnetic flux produced by the surrounding. This is, suppose this is a three phase. Three conductors are there. So when current passing through this, there is a magnetic flux linked with this. And the most of the magnetic flux is passing through the center point of the conductor through the inside. Here is the magnetic flux density is high at the center area. On the outer area, magnetic flux density is very less. So that means per unit area flux at the center area is more. So the inductance will be high. If the inductance is high, that means impedance of the conductor at the center area is high. That means the impedance along the cross section of the conductor impedance, AC impedance is not uniform. On the center area, impedance is high, then it gradually reduces and the surface impedance is low, or you can say in terms of resistance also at the low. That is called skin effect or proximity effect. That is called skin effect. Similarly, when the other conductor is locating nearby, then that magnetic flux also link with this. That is also has an impact on this cable, this conductor current carrying capacity. So due to this, what is happening? Most of the current is carrying by the surface of the conductor, and the rest of the area is not carrying any current. Automatically, conductor current carrying capacity get reduced. To improve this thing, suppose I need a 50 square millimeter, suppose this diameter is a 10 millimeter. So instead of one conductor of 10 millimeter dia, what do? We make a small conductor like this. Maybe it is a 2 millimeter dia. 2 millimeter, total is 10 millimeter dia, we put 5 like this. That will be 10 millimeter, 2 millimeter each, instead of 10 millimeter one. In that case, what will happen? These wires will be a smaller diameter. If a smaller diameter, center area will not carry any current, but surface area will carry current, but the effective current carrying area will be increased by this process, because now there are, instead of one, there will be multiple conductors. All the conductors, center point not carrying current, but surface is carrying current, but all the surface, if we add up, it will be more than this surface area. So by that way, we make the contact, we call it is called a strand. Each strand has some diameter. So by splitting the diameter, we can make the total conductor. Now this strand, how it is made and how many strands should be there, there is a formula for this. When we make this multi-strand conductor, so the conductor at the center point there will be one conductor at the center. That is the first conductor. Then first conductor, around the center conductor there will be, outside there will be a conductor. Now this first layer, this is called center conductor, we call it layer 1. Now the second layer, how many, suppose say layer 1, layer 3, layer 4, layer 5, like this. Now first layer only one conductor. Second layer, how many conductor will be there? That will be divided by 6 into n minus 1. So this is where n is the number of layer. Suppose in the second, this is if we consider this is a first layer or first conductor, then this is my second layer, we can consider in that way. If n is equal to 2, then 2 minus 1 means it will be 6 number conductor. In the second layer there are 6 conductor. In the layer 3, how many conductor? It will be 12 conductor. In the layer 4, n value 4, 4 minus 1 means 3, means 18 conductor. In the layer 5, how many? For layer 5 minus 4, 24 conductor. So if we have a conductor which is a center conductor, layer 1, then second level conductor, then we have a third level conductor. This type of three layer strand is there. Then how many total conductor will be there? First is 1, then plus 6, plus third layer 12. So total will be 19 conductor will be there. So in this case 19 conductor. If I have a conductor of main conductor which have a 4 layer of strand like this, then how many? This will be 19 plus the third level is a, fourth level is 18. 18 plus 9 means 37. There will be 37 conductor like this. Now out of this 37, as we say that ACSR conductor, we say ACSR conductor. In that case, what will have? Aluminium core is still reinforced. Aluminium conductor is still reinforced. In this case, what will happen? This all conductor, suppose the center conductor is steel, then this one is steel, rest of them are aluminium. But sometimes it may happen to increase the reinforcement. The center conductor itself can be contain of multiple strand. It may be one center, then outer side of a 6, total 7. That make one conductor. That is we put on the center. That is also sometimes possible. Suppose a conductor, we make a ACSR conductor or any type of conductor. It makes a center conductor. We made it with a suppose 6 strand outside and center strand 1. That is one strand. We make a very thin strand. We made it. Okay. Then suppose then total 7. So 7 conductor, maybe it is a 2.1 millimeter diameter. We write in this way. But outside maybe, then this is the first conductor. Outside maybe there are 3 layers are there. 12, 18, 6, 12 and 18. 12, 20, how much it is? It is a 36, right? So this will be 36. But maybe inside conductor will be maybe 3.1 millimeter. So we write down in this way, 36 number strand 3.1 and 7 number strand 2.1. The 7 number strand is the center strand, and outside we have this strand 18, 12 and 6. Okay, 6, 12, 18 in this way, 3 layer. So center layer is a one conductor, but that one conductor again make like this way. Or sometime it may happen, instead of that we make a 2 layer. One layer is a center conductor steel, then another 6 conductor is also steel. This part is still reinforced. Over that we maybe put 3 different layer. In that case, what will happen? This goes to steel, and then this 3 layer will come as a aluminium. Aluminium conductor steel. This 3 conductor means it is how much? 12 plus 18 plus 24. That means it is 34. It is a 30. It is a 54. So it will be coming 54. Suppose it is a 3.5 conductor. This outer aluminium conductor is a 3.5 millimeter dia, 54 numbers, and 7. Suppose it is a 2.1 or maybe 3.1 conductor. This way we can write down. This part is a reinforced part, and this part is the conducting part. Okay. So this way, this conductor is made not by the one conductor. To avoid the skin effect, we make this conductor in this way. Second point is this, when we make this is how this ACSR conductor or all aluminium conductor stranded are arranged. So this is the conductor arrangement. Now if we see the various conductor which we have, so there is a lot of conductors, but this conductor normally in case of overhead conductor, we do not mention the conductor by cross section area. We generally nomenclated the conductor by some brand name. Now in different country, this name is different. Some country they put the conductor name in terms of animals. Some country they put the conductor name in name of fruits. Some country they put name of flowers. There is a different tendency, strategy in different countries. But most of the Asian and Middle East, we use this conductor name in name of the animal's name. So I am putting some of the conductor name in the I am making a table. In that table, I am putting all the conductor details. Couple of conductor details. The way we nomenclated those conductors, the table is shown below. With this table, we will now discuss how this is done. From the table, you see this table, I am putting mainly whatever the major application. There are so many are there, but I have only captured couple of them only. Now, one we call the minimum size one is a squirrel. Then the second one we call is rabbit. Third one we call is a dog. Then it is called wolf. Then it is panther. Then goat. Then zebra. Then mouse. It is generally gradually increasing higher capacity and higher voltage, higher current capacity conductors. Now, in case of low voltage, this squirrel and rabbit we generally use for the low voltage or medium voltage. Up to 11 kV we use this. In the low voltage we use LV, which is a area of the cross section area is a 20 square millimeter is the cross section area of this squirrel conductor, and it can carry current at a 45 degree centigrade temperature up to 130 ampere. Okay, and then 130 ampere means it is, you can say, about approximately 100 about 80 kVA power. It can 80 kVA power it can carry approximately. And this conductor is there is a center one conductor, and there is a second layer. There are 6 conductor. All conductor diameter is 2.11. Now, in case of rabbit, it is used for the low voltage as well as up to 3.3 kV, 6.6 kV line, even 11 kV line. Sometimes we can use it. This is a cross section as a 50. It total capacity, current capacity 250 ampere. 250 ampere is divided by 1.6. It carry about 150 kVA power. It can carry. It is mainly used for the LV. Mainly LV purpose we use this conductor. And if you go for high voltage, medium voltage, it can go a higher value. In the low voltage, it can carry up to. If you go for 400 volt, it can carry about 150 kVA power. Okay, it can carry. And this configuration is same like this. There are 7 conductor, one center conductor. Outside the second layer, there is a 6 conductor. What do we say? 1, 6, 12, 18, 24. Then 5, 30. This is the configuration. 6 means center 1 conductor, outside 6 conductors. So total 7 conductor. The wall diameter is 3.15 millimeter. Now the third is a dog, which we use for the medium voltage and high voltage. Up to 66 kV we can use this dog conductor. This conductor cross section is 100 square millimeter. It can carry up to 350 ampere current, and we use for the medium up to 66 point we can use up to 25 MVA power we can carry it. This has a total 13 conductor. The first layer 1 conductor that is made actually 1 and outside 6 make it 1 conductor, that is a 1.57 millimeter dia, very thin millimeter dia, 1 conductor. But that conductor is not single, it is a multi-standard, total 7. And then the second layer is a 6 conductor. This conductor is a 4.92 millimeter dia. This conductor we call a dog conductor. Then the fourth conductor is a wolf, whose area is 150 square millimeter. Here there are total 3 layers because a center portion. The first layer and second layer is for the reinforcement purpose. That is a 7 conductor. Each conductor 2.59. Over that there are a third and fourth level. 12 and 18 conductor is 30. That 30 is that means outside conducting part is 30 strand, 2 layer, and center and the first layer used as a reinforcement purpose. All conductor size is 2.59 millimeter. Then after the dog there is a panther, which is used for the mainly 132 kV line we use for the panther. That panther cross section is 200 square. It is a cross section area. It can carry current up to 560 ampere, and it has also same thing. It has a center 1 plus 6. This 2 is for reinforcement purpose, and 12 or 18 for the conducting purpose. Total there are 4 layers, and all the conductor is a 2.59. Sorry, all are 3 millimeter diameter, and it can carry about 75 MVA power. This panther. Then the goat, which is used also for the same 132 kV, even for 220 kV, and it can carry about 100 to 150 MVA power, and that is also the same configuration 37. This is the same, only the conductor diameter instead of 3, it is a 3.7. Then we have a zebra, which is used for the 220 kV line. This is a cross section area is a 420 square millimeter. It can carry 850 ampere current, and its capacity is a, with the 65 degree, if you go 75 degree, it will be more, it will about 200 MVA power it can carry at a 220 kV level at zebra. And most conductor is a higher conductor. It is a same, it can carry, it is used for the 400 kV lines. It is most conductor used for the EHV line up to 400 kV and upward, and that conductor area is a 520 square millimeter. It can carry approximately 1000 ampere current, and that carry about 400 MVA power. So these are the various conductor we use as a trade name, and that is the use of the conductor. Now out of this various conductor, now we have to discuss another point. Now there is a there is one conductor called bundle conductor, that is also we use for the high voltage transmission purpose. Now you know why we use the bundle conductor. There is a phenomena in the overhead line called corona discharge. In the case of conductors, when the conductor is going through the tower, suppose this is a tower and this is a hanger and the conductor is hanging over here, suppose this is the conductor, there are three conductors this way, suppose this is one conductor, this is one, this is one, there is a gap between these two. Now due to this gap, there is a ER in between this. Now due to this ER, what is happening, you know, this ER can break down. Normally this system is designed for 30 kV per centimeter. 30 kV per centimeter, this is the your insulation value we consider for the dry air with a 1 atmospheric pressure at 35 degree centigrade 25 degree centigrade temperature and normal condition, that is the dry air. This is the insulation capacity of the air, 30 kV per centimeter, and based on that we distance or the porcelain distance or the insulation distance we decide. Now during rainy time, if this air density drop or there is a humidity in the air, then this automatically this 30 kV per centimeter air insulation capacity drop down. Then there will be there's a ultraviolet radiation with a hissing sound come from the transmission line, and that ultraviolet radiation with hissing sound we call it a corona. This corona, what is happening during this time, due to the weight here or the density, due to if the voltage goes up or the air density drop down, become more, then there is a humidity in the air. Then what will happen? This some of the air particle will get ionized, and due to the ionized, then this form a plasma, and due to the plasma there will be a conduction from one phase to other phase, and due to this conduction, this corona discharge or it form a plasma, and that plasma help to discharge this corona. So this corona, it depend on the various factors. One of the factors, as it depend on the distance between the two conductor, two phase, is also depend on the diameter of the conductor or radius of the conductor. So at what voltage, if you see this disruptive voltage, at what voltage this air will break down, there is a formula for that. If you see the disruptive voltage is a Vp, suppose V is the critical voltage at which the breakdown takes place, that depend on the phase voltage, how much phase voltage is there, divided by this delta. Delta means that is the air density into conductor smoothness, how the conductor is smooth. If it is a cylindrical conductor only, then M is 1. But if the conductor is not cylindrical, it is a stranded, then this M value will be more. Then into diameter, radius of the conductor into log D by R. D is a distance between the, suppose these are the two conductors, this is the distance of the conductor D, and this is a diameter, so half of the radius is the R. So this is R is the radius and D is the diameter. This is the equation for this is the critical voltage. Now when this voltage reaches to the critical voltage, then immediately a spark over 10 place. That means then this Vc become your 30 kV per second, 30 kV per centimeter. This critical disruptive voltage, if we call G0, then when Vc becomes G0, then this Vp become Vc. Okay. So from here you can calculate the disruptive voltage, how much it will be. The disruptive voltage Vc, that is equal to this critical voltage, that is 30 kV per centimeter. This into how much? Delta into M into R into log of D by R. You can see from here. That means this disruptive critical voltage, it depends, this is a 30 kV per centimeter. 30 kV per centimeter. It depends on the air density, polishness of the conductor and the conductor radius. So if you make a conductor bigger diameter, then that critical voltage will be more and more. Okay, disruptive voltage will be more. So immediately it will be breakdown. So it will be corona discharge will be more. Okay, this corona, then immediately as you increase the radius of the conductor, then automatically it is a proportional to this disruptive voltage on this critical disruptive voltage will be increasing as this delta is increasing. So when the air density increase, immediately the critical voltage will be increasing. If you increase the radius of the conductor, critical disruptive voltage will be increasing. So to reduce this thing, we have to reduce either the sigma delta or we have to reduce the R. That means if I reduce the R, then automatically disruptive voltage or the disruptive voltage will be reduced, and then this corona discharge will not take place. Okay, because this value, the moment it cross 30 kV per second, immediately disrupt start. So as you increase more and more, as this value increasing, this VC value will be increasing more and more, then this value will be automatically disruptive take place. So to reduce the disruption, we have to reduce all this delta M and R. Delta value will be 1 for the dry air. If it more than 1, then immediately disruptive take place, because this value will be more than 30 kV per centimeter. So that's why when you want to reduce the corona, one of the way to reduce the conductor radius, this conductor is a smaller diameter. So in the case of high voltage transmission, 220 kV or 400 kV or 800 kV or 1000 kV volt transmission, instead of single conductor, suppose this conductor requires suppose 1000 square millimeter. So instead of one conductor per phase, we put a, suppose maybe 3 conductor we are putting, and this conductor is connecting through a spacer, and this conductor maybe is as a 300 square millimeter. So 3 conductor will be, suppose this is 900 required, we put 3 conductor 300 square millimeter, and with the spacer we connect it. So instead of one big conductor, will be a smaller conductor, and these all are same phase. In that case, corona discharge will be less, or the corona discharge also, corona discharge will be less, because corona discharge is the wastage of energy, it loss of energy, the energy loss will be also less. That's why for the high voltage transmission, when the conductor size is very big, in that case, using of single stranded conductor, we use multiple conductor connected through the spacer per phase. That will reduce the corona discharge. This is one of the purpose why corona discharge rings and these are used. And another point we have to keep in mind, corona discharge also depend on the sharpness. You will see here, this M factor from the polished conductor, this M is 1, but if the conductor surface is not polished or there is sharp edge on the conductor, the M value will be higher and higher. That means immediately disruptive voltage will go up and immediately corona discharge will take place. That's why in the high voltage transmission on the any transmission line, any fine sharp edge will be minimized. No wire will be left out, no sharp edge will be there, all the sharp edge should be properly polished. That is another requirement for the to avoid the corona discharge. So these are the various overhead conductor details and how the conductor is designed, what is the business name. And for 3 voltage level, I am writing one formula for 132 kV, 220 kV and 400 kV. If you see the power carrying capacity, the power carrying capacity of this is depend on the current. Voltage is 132 kV. The current carrying capacity, if the I is the full load current in ampere, so it will be, if suppose 100 ampere current is going, it will carry how much power? 18.3 MVA. This is the capacity in MVA, current power carrying capacity. In 220 kV, this will be how much? That will be your 220 kV, it will be double, approximately double, it will be 0.305 I. And is 400 kV, it will be 0.554 I. I is the current in ampere, these are all MVA. So if you put this I value, corresponding I value, this will be the formula for 3 voltage level. At 132 kV, power MVA will be 0.183 I, 220 kV 0.30 I, and 400 kV 0.54 I. This is the shortest way to calculate the power at the various high voltage line. It is a HV and EHV level. So these are the 3 level power carrying capacity, and based on the current we can decide how much current for a particular MVA, how much current is required, and for that we have given the table starting from rabbit up to the moose, which conductor is fit for that. Suppose one moose conductor is not enough, then we have to put a 2 moose conductor with a spacer per phase to carry the required power. Suppose you want to carry in 400 kV line, you want to carry 600 MVA power. In that case, maybe 2 moose conductor is required. So we put 2 moose conductor with a spacer and connect it per phase. In that way, we can carry the higher amount of current. Now, how we calculate this conductor size and what are the various factors, which are the various external factors affect the conductor sizing, that we'll discuss in the second session. So second part of this session. So this is all about overhead conductor details and the conducting materials, their brand name, and this current carrying capacity, and why the conductor is different types. This is all about today. Then in the next part, we'll discuss about the conductor sizing. Thank you very much.